Good afternoon or good morning, everyone, depending on your location in the world. Welcome to our February American Segmental Bridge Institute lunchtime webinar. Today, we're excited to have Tim Berry of RS&H presenting for us. He's going to present on repair of the West Seattle Freeway Bridge. I am your guest host for today. My name is Wade Bonzen. I'm the chair of the ASBI Construction Practices Work Group, and Greg Freeby has asked me to sit in for him today, so happy to be here and looking forward to a great webinar. Just a couple of brief announcements before we get moving. Our March webinar is going to be on March 29th, same time, 12 o'clock Central Standard Time. And the topic is going to be a primer on lightweight concrete for bridges, presented by Dr. Reed Castrodale. So that should be a very interesting topic, very timely for our industry. Also wanted to announce that the ASBI grouting certification training is going to be held on April 24th, 2023. It's going to be conducted in person in Austin at the Commons Center at the J.J. Pickle Research Campus. Registration is currently open, and you can find that registration on the ASBI website under events. We're also looking forward to our 2023 convention and committee meetings. We are returning this year to Tucson, Arizona, at the Westin La Paloma Resort and Spa. Those of you who attended the convention a couple of years ago remember this venue. It's a great venue, beautiful area. So we're excited and looking forward to returning to Tucson. That's going to be November 5th through the 8th. Same basic schedule as previous years, committee meetings on the weekend and Monday morning, and then rolling into a bunch of seminar presentations after that. Also wanted to announce that we have a new ASBI publication. This is an updated report on the durability of segmental concrete bridges based on data from the National Bridge Inventory Database. This is a great report. We've released this report periodically over the years. This is the 5th edition, dated 2022. And this is available on the ASBI website under the Publications tab. So it's free to download, and there's a lot of great information on there about the durability of segmental concrete bridges. So before we get started, just a few instructions for the webinar. If you lose connection, you can rejoin the webinar in progress. And I'm going to let that screen catch up. Just use the link that you were provided when you originally registered in order to rejoin. You'll miss a little bit of content while you're away, but hopefully you can log back in fairly quickly. Certificates for attendance will only be issued to those meeting the minimum time required in the session, so make sure that you spend as much time in the session as you possibly can, and also make sure that the webinar window in your computer is active so that it gets counted as active time participating. Please allow about a week for attendance certificates to arrive via email. And we'll do a Q&A at the end of the presentation today. If you'd like to submit a question, you can submit these from your desktop application. You can submit these questions anytime during the session, and then we'll go through those questions at the end of Tim's presentation. So you can see here the instructions on the screen. You can find the little questions drop-down menu on your GoToWebinar application, and you can type your question in there, and then we'll go through those questions after the presentation. If you're on a mobile device, which is more and more common nowadays, the GoToWebinar app has a little small question mark icon in the upper right-hand corner. You can click on that and access a little text box to put in your presentation or your questions. This is the required RCEP slide, this particular presentation is accredited with RCEP, and as such, PDH certificates will be issued for this. So today's speaker is Tim Berry with RS&H, and the discussion is about the West Seattle Bridge repairs. Tim is Vice President and Senior Project Manager for RS&H. He has 23 years of experience in construction management of complex and segmental bridges across the country. And he's been a long-serving member of ASBI, very active with that organization. He currently serves as the chair of the grouting work group. And Tim is a graduate of Michigan Technological University and currently resides in Tucson, Arizona. So Tim, I'm going to turn over the presentation to you so we can get moving with your discussion.
Okay, thank you, Wade. Get loaded up here. Okay, hopefully everybody's seeing my screen okay. Should be loading up. Before I get started, this project in particular, the West Seattle Bridge repair, I know it's been talked about quite a bit inside ASBI, really over the last three or 4 years, with everything that's gone into this project and the bridge and everything that's happened to it. So the presentation today is really all about kind of telling the final story, how we were able to get the bridge back reopened, and the efforts, and I stress the word effort to get that accomplished. So some of you might be new to the project and not know about it. So we're going to talk a little bit about the background of the bridge itself. Talk about what the initial emergency repair plan was when we first ran into the difficulties of this bridge, and then really focus on what I call the final repair project, which occurred basically most of last year, 2022, and then how we were able to reopen the bridge. So a little bit of background, like I said, this is the West Seattle Bridge. It was opened in 1984. It crosses what is called the Duwamish River in Seattle. It connects the community of West Seattle, which is it's really the main thoroughfare and the only connection of that community to the rest of the city of Seattle. The bridge is owned by the Seattle Department of Transportation, and the three main spans, and the spans that we unfortunately had issues with, are cast in place balanced cantilever. And then the entire corridor is roughly 5,600 feet and carries 7 lanes. So we're going to focus only on the main span unit, the 3 spans in the center. So I mentioned West Seattle. In this photo here, you can see outlined in red. That's the community of West Seattle. It has roughly 82,000 people, so it's a pretty significant portion of the city of Seattle. And the dark red line there that you see is the West Seattle Bridge. So it's basically the main connection point between that community and downtown Seattle and the rest of Seattle proper. So this bridge is utilized. It's known as one of, if not the most utilized piece of infrastructure in the city of Seattle. It's important to commuters, to businesses, obviously, emergency services. And when under operation, it's 100,000 vehicles per day and 25,000 transit users per day. So it's a very significant piece of infrastructure to the city. I realize this kind of hard to see, but what the purpose of this picture is this is the detours that were required when the bridge was shut down. You can see up at the top where the bridge closing or the bridge crossing is. The next furthest south crossing of the Duwamish River is quite a bit away. And the thing that this does not illustrate as far as these detours is this is a very much urban residential area. 2-lane roads, on-street parking, a lot of traffic signals, and 25-mile-per-hour roadways. Definitely not conducive for 100,000 vehicles per day, and just not set up to handle that much traffic. So the inconvenience to this community really just cannot be overstated when the bridge is closed. So speaking of closing the bridge, what happened? How did we get to that point? So going back to 2018, when some cracking was originally observed in the web walls and in the floors of the bridge. It wasn't overly concerning at first, but it was noted and obviously noted that it needed to be monitored more closely. And then as inspections progressed over the next couple of years, it showed the cracks getting worse and unfortunately getting worse and worse over a shorter and shorter time frame. So in 2020, it was really noticed that the problem was accelerating pretty significantly. And the other alarming part is the cause was unknown. And this shows a pretty good indication of what we talk about when we talk about worsening in a short time frame. What you see in green were cracks were identified between 2013 and 2019. And then in orange, observed again in December now of 2019. So really only about 4 or 5 months after the fact. You see that what was in orange. In yellow, between December and then March 6th of 2020. So really only in 3 months. And then in blue, between March 6th and March 23rd. So you're talking less than 3 weeks. That's the additional cracking that was seen. So this is obviously when the alarms are starting to go off that there's a serious problem here that needs to be investigated further. And I mentioned before, this is actually a memo from the engineers that were monitoring the bridge, is that they couldn't model the cracking at the time they were seeing it. So cracks getting worse and getting exponentially worse in a short period of time, and unable to determine the cause. So really had no choice. They had to close the bridge for safety reasons. So that happened on March 23rd, 2020. The bridge was closed, and like I said, the major inconvenience to the city of Seattle. So the initial response after the closure of the bridge was to do a very quick emergency repair, basically to stop the cracking and sort of stabilize the structure after the traffic had been removed. So it was really 3 phases: to install some carbon fiber wrapping in the main span, also to install some new post tensioning, and also to do some epoxy injection of some of the cracks, not all of them, but certainly some of them. And I mentioned the carbon fiber wrapping, and then also to install this new post tensioning in the main span. And you can see these metal or these steel blocks were the essentially the makeshift anchors that they were able to install for this added post tension. And a very important piece of the emergency repairs was to install this bridge monitoring system, a series of strain gauges and electronics and even cameras, so they were able to monitor the bridge in real time and really see what was going on. And that was useful, obviously, at that time, and it was useful during the final repairs, and it'll be in place for the remainder of the life of the bridge. So after the emergency repairs, we're able to sort of stabilize things. Then the decision needed to be made. Is this bridge savable? Does it need to be repaired or replaced, or can it be repaired? And so a lot of thought was put into this. A panel of experts was assembled to take a look at this. And finally, after a lot of discussion and a lot of meeting, it was determined that yes, a repair could be developed and designed. And so that was the step forward for the Seattle Department of Transportation. So that brings us then to the repair contract. This was the project team for that repair contract. The CMGC delivery method was chosen by SDOT for a couple of reasons. One, for expediency, to deliver the project as fast as possible, and also with just the complex nature of what we needed to accomplish. Having the contractor on board early on in the design phase was really beneficial. Have them contribute to some of the methods that they were going to use, and having them as part of the design process was really helpful. So NTP for the project was in November, November 21st of 2021. The CMGC contractor was Kramer North America, 2 of their major subs, Structural Technologies and Valley Electric. And the EOR who was already on board was WSP for SDOT. And then selected a construction management firm, which was RS&H, with the subs KBA and JTS. So at that time, we had about 30% plans, and then about a budget of roughly $45 million. So one of the things that this recognized, obviously, was you have a completely closed corridor where we have to repair this bridge. So there was an opportunity to do some maintenance as well. So with this closed corridor and having no traffic to deal with, they made the decision to do some maintenance on what was, besides the segmental, the rest of these bridges were also more than 40 years old and in need of some maintenance. So They were able to do some, obviously repair some joints. This was all over the bridge, not just the segmental portion. Did a much needed deck overlay in a good portion of the approach spans. On the far eastern side of the project, on the West Seattle, excuse me, far western side of the West Seattle side, there's concrete pavement. We ended up replacing roughly 90 different panels of concrete pavement. And then new signs, new sign overhead structures, and a lot of what I call miscellaneous maintenance, because this was a pretty unique situation. You had a corridor that hadn't been driven on for over a year. So there was a lot of things that needed to be done to this corridor to get back into a condition where it could be driven on. And then, unfortunately, but not unique problem that was discovered shortly after the corridor was closed. It was found that all of the copper wiring for the entire lighting system of the corridor was stolen. They don't really know when it happened, but it was determined shortly after. So this was something that obviously had to be added to the scope. They needed to rewire all the lighting on the bridge. So something else fun to deal with that I'm sure many people on this webinar have experienced. So the final bridge repairs, as we enter into this, really broke down to three main parts of the scope, besides the maintenance, of course, that I mentioned. Number one, epoxy injection of the cracks. It would be impossible to epoxy inject all of them, so just a select number of the cracks needed to be injected. Some carbon fiber reinforced polymer wrapping at strategic points of the structure, and new post-tensioning infrastructure and new post-tensioning, which we'll get into a lot more detail on that a little bit later on. So for the crack injection, again, I mentioned it'd be impossible to get all the cracks. So a process was set up where the UR would actually come out and identify the cracks that should be injected, the ones that were most appropriate to be injected, the most critical ones. And so that process would take place. They'd identify the cracks, and the contractor would come in behind and then do the injection. It was really a good teamwork, good effort amongst all the players involved with the project to get this done and get it done quickly. When all told, we did end up injecting in roughly 13,000 linear feet of cracks in the structure. For the carbon fiber, this again was a strategic use of this technology, using carbon fiber laminate. Those of you who aren't familiar with carbon fiber, it's a really good use for this material for repairs, for for strategic points where you can bolster and increase a lot of the reinforcement of the structure itself. So you can see in this photo in yellow is where the carbon fiber was applied. It was applied both inside the box and on all exterior walls and exterior bottom of the segments and in between the two segments. This is a twin structure. So a lot of carbon fiber was installed. And there's a couple of reasons why this was used. One, it's relatively easy to install this. You don't need heavy equipment. It's not really that difficult. And another thing it did is you got a lot of beneficial use out of this material without adding a lot of extra weight to the structure. We're already dealing with a structure that's having major structural problems. So using carbon fiber wrapping was a really good solution to some of this. And you can see in this photos, this is the application, obviously inside the bridge. You'll see the carbon fiber wrapping running in two directions, both horizontally along the web wall and vertically. Depending on how it is oriented and how the fibers are oriented, it provides different force resistance and different applications. Then here you can see it on the exterior of the bridge as well, some of the application. And all told, when we were complete, we were roughly 51,000 square feet of carbon fiber wrapping on this project. So as you can see from the pictures, and anybody who's ever seen this bridge, the biggest challenge for both the epoxy injection and for the carbon fiber was access. This is an incredibly tall bridge. It crosses over a channel. It crosses over rail lines. Not very easy to access, and especially since all exterior surfaces of the box had to have carbon fiber and epoxy injection both done. So the solution that the contractor came up with was actually worked fantastic. These inspection platforms that were hung from the structure, and they were mobile as well. They had a pretty simple winch system that's set up on top of the deck, and they were able to move these platforms up and down the entire span to wherever they needed to go. And that was really important because of the locations of the cracking and the carbon fiber, you had to be able to move and move quickly, but also have a crew be able to work relatively efficiently. Just the use of a bucket truck or something like that would be fine, but you're going to be constantly moving the bucket truck. You can only get 2 people in it max. You don't have the room to work, and it would be a lot of extra steps. With this, you can put the entire crew, all their equipment, and everything on the platform, and it's mobile. And another thing is weather considerations. Anybody who's spent any time in Seattle in the late winter and the fall knows that weather is always a problem. You're always going to have rain. You're going to have cooler temperatures. So with these inspection platforms, they're able to encase it with plastic, and then through the use of heaters, you had a perfectly viable working conditions inside this structure, so the entire crew could work. Like I said, all their equipment, everything, and maintain environmental conditions that were necessary for the application. So this was a great use of these inspection platforms to be able to accomplish this work. So moving on to what was really the main part of the repair, and certainly the most difficult, was installing the new post-tension tendons to bolster all 3 spans. You can see here from this table, these were not insignificant tendons that we were adding. We had a series of 19 strand tendons in the end spans, what I call the end spans, 2 outer spans of the main 3-span unit. And in the main span, 27 strand tendons that carried over 1 million pounds of force. So these were not insignificant. And anybody who's ever done any sort of bridge rehab or repair job knows that, as soon as you get in there, you really just don't know what you're going to have until you start opening things up. The plan is great, and everything can be planned out as best you can, but until you start get in there and seeing what you're dealing with, you just don't know. And in this bridge in particular, because of some of the difficulties that we're going to be to install this post tensioning, in particular, we had to core the existing structure. There were 32 locations where we had to do 17-foot long 6-inch cores to be able to install these tendons. And there were 8 locations where we had to do 6-foot long 6-inch cores. So that alone is incredibly difficult to accomplish. This is, again, obviously an existing structure. We had to core through diaphragm walls that had obviously reinforcing steel. It had existing post tensioning from the original design. And of course, nothing is where it's supposed to be in accordance with the original plans. And so it was a constant battle of trying to find where we could actually get this core to do the minimal amount of damage to the existing structure. We had to install new concrete structures inside the box to be able to accommodate this post tension. That means anchor blocks, that means deviator walls, and support blocks that all have to be installed inside the box with limited mobility, limited equipment, and limited access. And all told, the new PT tendons, 16 19-strand tendons and 8 27-strand tendons. So with the coring, those of us who understand and are involved with post tensioning knows that the location of the anchor and the path of the tendons is incredibly important. That's what provides, it's providing the forces that you need for the design. So where these cores were located was incredibly important. And again, as per the original design, we had an exact location where these cores need to be. However, the first step of coring was GPR scan. So we had to get in there and GPR scan where these cores were going to go to make sure we avoided as much of the existing reinforcing steel as we could, and avoided all of the post tensioning that was existed. So what we found is where the cores are supposed to be wasn't going to work. There's too many things in the way. So then the core location would have to move. And then, of course, once you move that location, your anchor head moves slightly, your path might be a little bit different. So every time you change just a little bit of the core location, it's going to affect that entire tendon. And it's going to affect the anchor on the other side. So you kind of end up chasing your tail a little bit. We need to move it here. Well, what does that do to the other side? Well, if we move it back over here, then it moves this. And so this was a very tedious iterative process to get this completed. So the next step after the GPR scanning was to do the cores themselves. And I will say that the contractor did a great job of maintaining the location within a pretty tight tolerance. A 17-foot long 6-inch core is pretty difficult to achieve, and to make sure you stay within an inch or so tolerance to make sure it stays in the right place. And this is an example of one of the cores from the plans, as I mentioned, 17 feet long, and like I said, the contractor did a great job. And I also forgot to mention that the majority of these cores occurred at the top of the diaphragm walls. So this is, roughly 20 feet off the surface inside the bridge. So it just made it that much more difficult for access and that much more difficult to accomplish being up on scaffolding 20 feet in the air inside a box with limited accessibility. With the concrete infrastructure for these tendons, again, a lot of different challenges presented itself to be able to do this. Because you're obviously inside the box, you have no heavy equipment you can use, no real equipment of any kind. Everything had to be hauled in by hand, had to be moved around by hand, and built by hand. So you have an incredible amount of reinforcing steel, all the formwork and everything had to be carried down, lowered down into the box, and then moved around by hand. So um, pretty difficult to achieve and difficult to get this done. And the theme you're going to hear me say more and more throughout this presentation is time was a huge factor for this entire project. Getting the bridge reopened was the number one goal in everybody's mind. So time was constantly and continually a factor. So building these, this is a picture of the deviator walls. These deviator walls, just for reference, anytime the tendon path deviates for these external tendons, you have to have this internal concrete structure that carries that load and carries those forces. So these are incredibly important, and they have a lot of force acting on them when those tendons become stressed. So this is something that has to be done correctly. You don't have any room for problems, for honeycombs, for voids. This concrete has to be placed, and it has to be placed incredibly well. And as you can see from the photo, they go all the way to the top, and there's no way to. It doesn't look like there's any way to get concrete in there. Actually, pouring the concrete was difficult as well, because the only way to do it, you can see it right here. There is a little hole in the ceiling there, and that was the only access available to get the concrete into the structure. So, proper vibration, proper consolidation of concrete is a major concern with pouring a structure like this with the limited accessibility that we had. And here you can see this is a picture of how we actually did it. The concrete pump was actually able, you had just enough room to stick the pump hose down through the hole and fill the formwork best they could. And then one of the things they did with the forming system is they put in these windows here at lower location and upper location. So this allowed accessibility from the vibrator to make sure that these walls were poured properly and didn't have any of those void issues or consolidation issues that we feared. And I must say, they turned out fantastic. Contractors did a great job. Really, really, really good quality concrete. No issues at all with these deviator walls. And so they turned out great, as you can see from the photos. And I also, by the way, forgot to mention, what you see above here is actually a drainage line running through the deviator wall. The tendons are actually right, the two ducts you see right below, and then you also have other utilities that dance around. So all kinds of stuff that had to be worked around to be able to get this infrastructure installed. So besides the deviator walls, another really important part was the anchor blocks. So again, we're installing brand new tendons inside an existing structure that carry an immense amount of force. You can't just slap a tendon inside there or just install an anchor block to the side of the wall to carry that much force. So these were pretty significant structures. This is one of the smaller tendons, one of the anchor locations at the end span. And you can see the amount of reinforcing steel, pretty incredible. And again, we're dealing with this inside the box with no equipment really to use whatsoever. But they had to be doweled in, of course, to the existing structure to be able to provide some sort of anchoring to the bridge. So now we're back to GPR scanning once again, and of course trying to avoid all the reinforcing steel and everything else that's inside that wall. So the intended location of all those dowels, there's no chance they were all going to fit properly with the existing reinforcing steel. So had to move a lot of stuff around, had to adjust on the fly to get it to all fit. And just doweling in wasn't enough. With the jacking force for these tendons were somewhere around 700 kips. So that's a lot of force that has to be carried. So just putting this block and attaching it to the wall wasn't enough resistance. So what you see in these blockouts here were vertical post-tension bars and horizontal post-tension bars that had to be stressed to be able to help further attach these blocks to this existing structure itself. And those bars daylighted out to the exterior, so it had to be cored all the way through the web wall and cored all the way through the bottom slab to be able to provide that resistance so that these anchor blocks could do their job. And this is kind of tough to see in this photo, but this is another anchor block at a different tendon location where this block right here was actually cast right up against the existing diaphragm. So this is where the 17-foot core, and the other side of this added block is where that 17-foot core location was. But in order to provide a proper anchor location and be able to provide bursting steel necessary for this anchor location, a block had to be built and added on to the existing diaphragm. So a lot of effort had to be done before we even thought about doing any of the actual brand new post tensioning to be able to build the infrastructure first and then be able to stress the tendon. And the tendon stressing itself was a challenge in its own right. As I mentioned before, obviously no heavy equipment of any kind inside the bridge, and really, or on top of the bridge. There was because of the structural problems, there was a rule that nothing over 10,000 pound gross vehicle weight could be on the bridge, could cross over the main span. So we couldn't have cranes, we couldn't have heavy pieces of equipment to move around the jack. So the decision was made by the contractor to stress these tendons with a monostrand jack. So you can kind of see it in the photo here. There's a monostrand jack sitting on this one tendon prior to installation. So what that means is, it can be done, but with a multi-strand jack, it's so much faster and so much more efficient. But because of the nature of this project, it would have been incredibly difficult to try to move a jack around, to try to raise it 20 feet up off the ground, and with the limited mobility that we had inside the bridge. So we stressed every tendon with a monostrand jack, and it was an incredibly tedious process, especially for the 27 strand tendons. Those tendons were over 600 feet long. So every tendon, of course, had to be stressed up to 20% first, which you always do. So that means 27 times you're stressing up to 20%. And then you have to go back and check each one to make sure they didn't lose force as you stress the progressing strand. And then for the final stressing up to 100%, it was 4 additional bites for every single strand. So 27 times 4, and that's how long it took to stress one tendon. So it was tedious and it was time consuming, but it was the right way to do it. And fortunately, it worked out really well. The post tensioning went incredibly well, and the bridge responded exactly how they were hoping, and went good. But it was a long, drawn out process. So because this project wasn't challenging enough, we ran into a few other issues that we had to deal with in trying to get this project done. And just for timeline, which we're going to get into here in a little bit, the construction started in basically January of 2022. We had NTP in November, but by the time the design was progressed and they were ready to go, it was January 2022. So we were still in the late stages of COVID impacts, of course. We had a couple times where we had some workers or crew members test positive, so we had people out and had to deal with that. One thing that was a major issue that we ran into is in the city of Seattle, actually starting long before we started any of our construction, there was a citywide ongoing Teamster strike by the concrete truck drivers. And so up until I believe it was about May of 2022, we could not get any concrete delivered to the project. And this was not just us. This is this is citywide. This is everywhere in the city of Seattle. So this was something that was sort of always hanging over our head as we were progressing. And the initial stage of the project was the epoxy injection and the carbon fiber, but there was a time where we knew we would eventually need to place concrete. And it would have been nice to do some of the maintenance work early on, maybe some of the overlay, some of that work. But since we couldn't get concrete, none of that work could be done. And as we got closer and closer to basically our drop dead date of where the project was really going to be in peril, the contractor did a really good job of mitigating these delays. They basically everything for the entire job was formed up and ready to go, and so it impacted how they intended to build the original project. Um, and so they had to basically just keep putting up concrete, keep putting up concrete, and then finally in May, there was at least a somewhat of an agreement between the Teamsters and the concrete producers that we were able to start getting concrete in May, and it wasn't going to be long before we would have been in serious schedule difficulty with the project and really would have started impacting us. It did impact us, but through a lot of effort by the contractor, we were able to mitigate a lot of those issues. Just again, because that's how thing goes. There's a peregrine falcon that nested on the bridge, basically right in the middle of our project. You can see in the bottom left photo, it was right on top of the piers of one of the end spans. So that inspection platform had to maintain safe distance away from the falcon. The workers had to be very careful about working anywhere close to the nest. And again, they were able to work around it through uh, through some delicate work and a lot of mitigation efforts. It didn't end up affecting us too badly, but it was just one more thing to have to deal with while we're sitting here, basically racing the clock to try to get this project open. Um, Again, this was 2022, so we had our share of material and supply chain issues, but it was one of those things where we just couldn't have supply chain problems affect our schedule. We didn't have a choice. It couldn't happen. This project had to be turned around as quickly as possible. So a lot of times the contractor would order materials before they got approved just because they had to. They didn't have a 6 month delay to any sort of material would be devastating for the project. So we couldn't afford issues like that. So a lot of effort was made to get submittals approved, to get things pushed through as fast as possible, to get materials ordered and just get material to the site as soon as we possibly could. And besides all that, this was by far the most intense media, community, and political scrutiny I have ever seen in a project. Um, there were daily, weekly reports to the public. Obviously, the public had a huge interest in understanding what was going on with this project and when the project was going to be reopened. One thing I'll add that added to this pressure and added to the scrutiny was um, there was a promise made by the now previous mayor of Seattle that before we stepped foot on the project, before we even started in January of 2022, the mayor had promised the people of Seattle that the bridge would be reopened by June 30th, 2022. And we quickly realized when we stepped foot on the project that that was never going to happen. June was just way too soon. It was too much work to get done in essentially 6 months, 7 months, and so that was just never going to happen. So starting around May, we had to break the news to SDOT that June was a pipe dream. It was not going to happen, and they said they understand. That's fine. They kind of knew that, but with the caveat, they said, but you need to give us a date. We need to tell the public when is this bridge going to be open. And this was in May, June of 2022. So after thinking about it as a project team, we sort of came up with the week of September 12th was what we promised SDOT and what they in turn promised the people of Seattle. So we figured that gave us a little bit of wiggle room. We weren't willing to commit to a specific date just because there was so much work that was left to be done. But we were able to at least commit to a week that we thought we could achieve. And so that was basically what kicked off our race to finish this project and to get this done. So this was essentially after the post-tensioning was complete. We finally stressed the last of our tendons. This was in July, in late July, and so this was the list of work that still had to be done, and why we were terrified to promise the city of Seattle an actual date at this point, because this is everything that still needed to be done. And obviously, this list is incredibly long, and oftentimes in construction, when we see that we have a lot of work that needs to be due and we need to compress a schedule, sometimes there's certain things you can do. You can increase your manpower. You can try to do simultaneous operations. But really, with the nature of this project, we couldn't do a lot of that just because this was such a linear scope and such a linear list of activities. Everything had to be done in order, and we couldn't do a lot of operations simultaneously. And I'll explain what I mean by that. So these are the final operations that needed to be done after the PT work was completed. It was actually dictated in the design that there was another phase of epoxy injection and carbon fiber wrapping that couldn't be done until the post-tensioning was done for design, for structural reasons. The PT had to be done first, and then what we called phase 4 of the epoxy injection and carbon fiber. So that just we had to wait. The subcontractor just had to sit and wait until the PT was done, and then once it was done, they could go and get back to work. So we had the final phase of the CFRP, and because they were using these platforms, obviously, for this work, because much of this was on the exterior of the bridge, those platforms couldn't be lowered, and that was a significant part of the project of getting those platforms lowered and out of the way. So that work had to wait till finally the CFRP and the epoxy injection was complete, so we could finally remove the platforms. Finish all the interior work. This is a lot more significant than it sounds like. There had been work ongoing inside this bridge for basically 2 years at this point. So there was, just an unbelievable amount of equipment and materials and everything you can think of down inside that box. Well, it all had to be removed. It all had to be cleaned out of there. And so this was a pretty monumental effort that needed to be started. I showed pictures of these before. This was the pretty extensive scaffolding system so that they could do all that work up top, install the post-tensioning, do the grouting, by the way. The grouting to post-tensioning had to be complete before we could remove the scaffolding system, all the forming materials, everything. And everything had to be taken out of the bridge out of a couple of access holes that you see at the very top of this photo here. That was the access that we had. There were 3 of those per bridge, per box. That was the only way to get this material in and out of the bridge. And like I said, it could only be lowered in and out with the forklift. We didn't have a crane, didn't have a boom truck or anything like that. And it was all done with forklift and by people carrying them up and down ladders to get out of the bridge. So again, the limited accessibility really made things difficult, including the cleanup, which is something you would think of as an afterthought. But there was a lot of cleanup, and getting these large materials out of there was pretty difficult. And then there was another part of the scope that was a great idea, and that was installation of these inspection platforms. So because obviously this bridge is going to be inspected pretty heavily for the remainder of its life, and because of the size, just the sheer size of the box inside, these inspection platforms were developed to give maintenance and inspection folks access to the wood walls and to everything. So it's great. It's a great idea, but this all had to be installed prior to opening of the bridge, and I'll explain why that is in a second. And it all had to be now where it's of course attached to the web walls. So we're back to doing GPR scanning and then finding areas where this material could be attached, and it all had to be installed after the post-tensioning was complete, after the grouting was complete, after the scaffolding was moved out of the way, and the majority of the equipment and materials were cleaned out of the bridge. And then these access holes that I showed in that previous photo obviously were temporary, so they had to be closed back up. They were all inside the travel ways, inside the lanes of the traffic, so they had to be repaired and closed up. And why this was significant, and why this closing up these access hatches had to be done at the very last minute, is because of the height of this bridge. Once those temporary access hatches that were opened up only for this project and only for the repair, once those were closed up, this was the only access inside the bridge, was manholes. There's 2 of these in each of the twin structures. And so any type of large equipment, any type of anything long, this was the only way in and out of the bridge. So basically, when we closed up those temporary hatches, everything that needed to be in the bridge better be in the bridge, and anything that needed to be out of the bridge had to be out of the bridge, because this was very, very inaccessible. You can see where it lies in relation to the yellow line there. So it's basically, to access this, you need a lane closure to be able to do it safely, and you're just not getting anything large or anything difficult in and out. So that's why one of the very last things we did was close up those temporary access hatches to make sure we got all the equipment in and out that needed to be done. And I also mentioned before how great those inspection platforms were, and they were essential to getting the project done. However, each one of those hanging bars that the inspection platforms hung from daylighted out the top of the deck, and what you see these little squares is this is the location of every one of those hanging bars. So again, all of these needed to be repaired. You can see they fall perfectly right inside the wheel paths of some of the lanes. So this was a pretty big effort to repair all these before the bridge could be open. And again, it couldn't be done early. We couldn't start doing it until the inspection platforms were lowered. And then a pretty significant part of this entire project was the physical load rating of the bridge that we did. This was going to be the final determination of whether or not this bridge would be actually reopened to the public. With the post-tensioning and all the work complete, and of course the bridge monitoring system in place, there was a process to physically load rate the bridge, and it wasn't just static loading. It was also it was dynamic loading. We actually had 3 different scenarios, 3 different speeds where they ran these loaded dump trucks across the structure, and then monitored the bridge to see how it reacted. And this report would be the final, like I said, the final determination of whether the bridge would be reopened. And just to give you an idea, again, a timeline, we now were targeting, basically, it was Saturday, September 18th for opening of the bridge. Still within our 1 week window of the 12th. So we were pretty happy that we still made that, what we said, the week of the 12th. This load rating was done the Tuesday before. And so that's how close we were cutting it. That load rating was going to get done, report processed, and then ASBI make the final decision basically on that Thursday before of whether this bridge could be reopened or not. And so it was down to the wire. And so all the work had to be done. Everything on the surface of the bridge had to be done with the exception of final cleanup and some final striping, etc. And I'm happy to report that the load rating was an incredible success. It actually performed better than they had modeled, better than they anticipated. So it was clear that when the load rating was complete, the report was finalized, that the repair work had done its job, and it was an incredible success. Just as an aside, and for you bridge nerds out there and who love your bridge history, the load rating of the bridge, it was reminded me by one of my colleagues when I mentioned what we were doing. And they said to me, well, just like the Brooklyn Bridge and the elephants. And my initial response was, what are you talking about? I didn't know what you were talking about. And I actually looked it up. It's a true story that the Brooklyn Bridge, when it was open in New York, the people in New York had a lot of consternation and a lot of concern about the viability of the bridge and was it structurally safe. And a lot of people weren't using the bridge. And so in part as a stunt and in part in response to the people's reluctance to use the bridge, they actually, I think it was P.T. Barnum brought his team of elephants, literally a team of elements, marched them across the Brooklyn Bridge to prove to the people of New York that it was safe to use and it was safe for them to use. So in a weird scenario, we kind of did the same thing. With the absence of elephants, we used loaded trucks instead. But I thought that was a funny story, and if you want to look it up, it's actually a pretty fascinating story that actually happened in 1884 on the Brooklyn Bridge. So anyway, that aside, once we finally had the go-ahead and the bridge was load rated and deemed safe to use, there was still some final touch-up work. We basically were down to now hours before. We had to make sure all the signs were in place. We had to close up some temporary barrier wall that had been opened up. We had restriped the whole entire structure, and then a lot of just routine maintenance, new guardrail. I mentioned the tree trimming that had to be done on the bushes just because this is an overgrown corridor at this point. FDOT mobilized a lot of their crews, did a lot of cleanup, a lot of these tree trimming, a lot of, there was basically for about a week straight, there was vacuum trucks and water trucks cleaning out the bridge. Because that was the other thing. I mean, again, over 2 years of work was being done on this structure. So all the tools and all the construction debris, everything had to be cleaned up to get this corridor usable again by the traveling public. So literally teams of people walked every square inch of this structure, every off ramp, every on ramp, to make sure it was safe, everything was clean and ready to go. And then finally, this was actually from the Seattle Times on September 19th, the front page, but we actually reopened the bridge. It was September 18th, 2022. what turned out to be 909 days that this structure was closed. And so obviously a pretty significant accomplishment for the people involved with the project, but also for the city of Seattle as well. And just to give you an idea of what we did and how we did it, there was 13,000 linear feet of crack injection. There was 51,000 square feet of CFRP wrapping. There was 250,000 linear feet of post-tension strand installed, stressed, grouted. There was all that maintenance work that I talked about throughout the entire corridor. Approximately $40 million of the work in less than 9 months. And if you think about that, that is a pretty incredible feat to be able to accomplish that. And just want to mention that a lot of the people that were able to make that happen. SDOT's team of their design people, their construction people, their maintenance people, the amount of effort that went into reviewing submittals, putting the contractor in a position to succeed, honestly, it was a big deal. The people that were involved with reviewing submittals, I can tell you, the basic rule of thumb for any submittal on the entire project, whether it was material submittal, whatever it was it had to be turned around and approved within 2 days. We didn't talk about weeks or months. It was days and hours. It was not uncommon to get contractors submitting things at 9 o'clock on a Saturday night, at 2 a.m. on a Sunday morning. It didn't matter. Like, it was just whatever it took to get the job done. So SDOT's team was amazing. Kramer's crew did really good work. WSP's team being available. I talked about the process for the crack injection, just having people basically available around the clock, reviewing submittals, turning stuff around, because time was such an important factor. We couldn't afford to have anything linger. We tried to solve problems as fast as possible. So just want to make sure I mention all the people that were involved with getting this project done, getting it done what I'll call on time. We made it within the window that we promised. So it was, at the end of the day, a success, and glad to have the project over and open. So with that, I'll close with two pretty nice views from the top of that bridge. Anybody who's been to Seattle can identify what those views are. And that's it. And looks like we got a little bit of time for a few questions if there are any. So Wade, back to you.
Great presentation, Tim. Thank you very much. We've got a number of questions, and we've got a little bit of time to go through those. Okay. So there are several questions here that are kind of all asking the same thing, and I know you were leading the construction management team, but could you talk a little bit about the source of the cracking? What was determined to be the source or cause of the distress in the bridge?
Yeah, I'll try to summarize this again. I will preface this, I'm not a design engineer, and I was not involved with the design of the repair. But it essentially boils down to, this bridge was designed in the late 70s, built in the late 70s, early 80s, and the original design just didn't quite accommodate its needs. Probably didn't take into account the type of loads that we see nowadays. And I think I hate to say that it was designed incorrectly, but I think that's basically what it was. It just wasn't the existing design, the existing post-tensioning, especially in that main span, just wasn't sufficient enough throughout the life, through the long term, through the creep and shrinkage. I know that I think the tenant experienced some relaxing over time, and I think it just wasn't quite sufficient enough, and wasn't designed up to the standards that we see nowadays. It was really what it boiled down. It wasn't any sort of incident. It wasn't sort of major thing that occurred or anything like that. No failure of a tendon, nothing like that. It's just, I think it just wasn't quite a sufficient enough design originally. And then once it got to a certain point in its life, it started seeing this cracking.
Okay, thank you. This is kind of a statistics question, but do you have a sense of how much more PT was added to the structure as a percentage of the original post-tensioning that was in the original bridge?
I don't know a percentage, but this was built by it was built cast in place by the balanced cantilever method. So that means it had top slab tendons and plus bottom slab tendons in the existing structure, and of course transverse tendons throughout the deck. There were no existing external tendons in the structure, so So all that was added was new, was external. I would guess maybe 10 to 15% of the original, but pretty significant because they went, you know, they were external drape tendons that basically went from pier to pier. And like I mentioned, for the main span, that was 600 feet of new tendons. So I would say, and just a pure guess, I would say maybe 15%. But I really don't know. It actually would be something to calculate. And unfortunately, it was. I will add it was the existing plans. I think SDOT did have copies of the existing plans, but it's one of those things. The bridge was built so long ago, they weren't entirely sure how accurate they were. So a full accounting of the existing bridge post-tensioning probably would be pretty difficult to do. But that's a good question.
Okay, great, thanks. So the monostrand stressing of those multi-strand tendons was an
Mhm.
interesting operation.
Yes,
Can you
it
talk
was.
a little bit more about the special measures that you all did when you were doing that monostrand stressing and even installing the strands themselves? What kind of measures did you take to try to make sure the strands weren't tangled up in each other and that you were able to get, an essentially equivalent force on each of the strands in that tendon?
Yeah. And that was the concern of monostrand stressing those is to ensure that you got the same amount of force in each strand. So as far as the installation, it was pretty standard. They just use a strand pusher that you would see on any other job. There's really not much you can do to try to prevent the strands from becoming tangled. They're going to do kind of what they want to do, especially when you install the anchor heads. But what we did is both for the 20% phase and then for the final 100% phase is we would stress every one of them up to 20%, and we would actually go back. At the beginning, we would get back on every single one and basically do a lift off to make sure we didn't lose any force. And we'd see every now and then that we did lose a little bit of force on some of them, so we'd stress them back up to that 20% number. And then when we were confident they were all at 20%, we had to do similar for the 100%. When we stressed each strand up to 100%, we then went back and at least 10% of them we would do a lift off on. And what we found is pretty much the lift off showed they didn't lose a lot of force for the 100% stressing. A couple maybe here and there would lose a couple 100 pounds, but we did make sure we did a lift off on a significant number of every single one just to make sure we weren't losing any force. So that sort of added to how tedious it was, because it wasn't just the initial pull 27 times and then 4 times 27. We then had to get back on them as well to make sure. But that would, if anybody ever does undertake something like that, it's essential to do that because you will lose some force, especially on the first couple that you stress. As you stress the subsequent tendons, you will lose a little bit, and so you have to check and go back and make sure.
Yeah, did you all do elongation measurements on the strands? Like,
Yeah.
did you try to do those on
Yep.
each and every strand or a portion of them?
We did it on every strand. We measured every single strand. So yeah, we did our theoretical calculations to make sure we understood what the theoretical elongation for each individual strand would be, and we checked every one and made sure every one fell within the plus or minus 7%. And like I said, we're a little bit lucky, and these are relatively flat. They're completely straight and pretty flat tendons, so there was not a lot of sweeps in them. So there was not a lot of friction loss really at all in them. So that actually made it easier. If you had some pretty serious bends, we'd probably see a little bit more difficulty in doing that. But these are relatively flat and straight, so it did make it a little bit easier.
Okay, great. And did the bridge have any provisions for future post-tensioning in its original design? And if so, did you guys take advantage of those?
It did not. It did not. So no, that's why unfortunately we had to do the amount of coring that we did. Um, there wasn't really any possibility to use any future, and it's a good reason why in the bridges we build nowadays that you see that it would have been incredibly valuable.
So you mentioned that some of the carbon fiber wrapping had to occur before final post-tensioning. Talk a little bit more about the sequence of the carbon fiber wrapping versus the PT sort of throughout the whole thing.
Yeah, it was very specific in the phasing. There was, and again, I'm not going to be able to do it justice. I'm not is not a design engineer, but there was the first phase had to be done, very specifically prior to the post tensioning, and then once the post tensioning complete, the final phase, and I'm sure others would be able to explain this better. It just has to do with, applying the force, basically because the structure is going into tension. That was part of the problem, especially in the main span. Being able to reinforce with the new post tensioning, basically getting the structure, back into compression, and then applying the carbon fiber wrapping is just sort of like an added structural strengthening at those strategic locations. So, but yeah, it was very particular, the order of operations that we had to do it. There was 2 separate phases of carbon fiber.
Okay, great. Here's another question. Did before the repairs got started, did the bridge have power and lighting inside the box girders already?
That is a good question. I don't think it did, but I honestly I do not know. By the time I arrived there, there had already been a year's worth of work inside there. I don't believe it had existing lighting. If it did, it was probably pretty minimal. There was new lighting installed. We upgraded all that, obviously, with the amount of maintenance that's going to be done on the structure and the amount of inspection moving forward. But I don't believe it did.
Okay, so part of the scope of that repair work was to not only install those access platforms, but also install permanent lighting. And did you have permanent power
Yes.
receptacles in there too?
Yes. Yep. Correct. Yeah. All that. Again, obviously, this bridge is gonna garner a lot of attention in its future.
Yeah. All right. During the process of the looking at the repairs, do you know if there was any discussion about doing any or need for any seismic upgrades to the bridge?
Upgrades? No, it was already designed. I think it was retrofitted actually, previously for seismic upgrades. So it had seismic protection already in the structure. So we did not. I mean, I would assume the design. I'm not going to speak for the designers, but I would assume the design took into account seismic, obviously, when they developed the design of the repair. But the structure itself did have seismic protection already in the structure itself.
So the large concrete post-tensioning deviators that you all installed during the repair procedure, did you all do any quality control or quality assurance to those after casting, like any kind of non-destructive testing to make sure you had, good consolidation and all that?
Not anything beyond typical just visual inspection. Because they weren't really thick, and you were able to see that the final structure pretty significantly. We were pretty confident with the measures they took. I didn't get into a lot of the details. They actually used some external vibrators. They did a good job of, of casting those, and we were pretty confident they were done really well, and that they didn't have any sort of void or honeycombing issues.
Okay, so we're just a few minutes past the hour, but we've got just a few questions that we can finish up.
Sure.
So those of you that would like to stick around and listen to those last few questions and answers, you're more than welcome to, but certainly we understand if anybody needs to hop off due to time limitations. One of those last remaining questions, what type of trucks were used for the load rating, and were they loaded to attempt to match a design load like HL93?
They were just dump trucks with the added trailers on them, loaded with. They had to be loaded to a certain amount of weight. That was really all that was prescribed. And they were, as far as the weight was prescribed, so that was and every truck was weighed prior to appearing on the site. So that was actually done pretty meticulously. And then they were staged in different. There was actually 7 different stages that I assume matched the loading conditions of the bridge. So there was somewhere, it was three of the conditions were dynamic, and the rest were static. So basically, all in this lane, kind of balanced between the 2 lanes. So it was, I think it was more of the different staging of the trucks that try to mimic the different loading conditions, but they all had the same amount of weight in them. I don't remember what that weight was, but they were just basically standard dump trucks with trailers with just dirt, just fill material in the back, but they all had to be a specific weight.
Okay. And this is an interesting policy question. So when the bridge was closed to traffic, do you know if there was any discussion about allowing mass transit to cross the bridge in a controlled manner, say, like loading up a bus full of people and driving one across at a time, sort of thing, just to try to
So
maintain some sort of access?
no, that's a good question actually, and uh, actually that crossing, you couldn't see it from any of the pictures, and maybe you might have noticed. There's a second bridge, a much lower bridge, that's only a total of 2 lanes that actually crosses the Duwamish. It's a segmental swing bridge. It's actually a pretty amazing bridge. Um, it under normal conditions is open to the public. When we had to close the high bridge, that bridge became basically permitted only, and it was only basically for transit and for emergency services. It couldn't possibly be used. One of the reasons it couldn't be used for all traffic is because it was literally only one lane each direction, so you'd be replacing, essentially a 7-lane bridge with a 2-lane bridge, and just it wouldn't be able to handle the traffic. And it's a swing bridge, which opens pretty constantly. So the decision was made that it would be permitted only for transit emergency services. So that was how they got around that. So there was some transit that was able to still operate, and of course emergency services were more important. They actually could get out to West Seattle pretty efficiently.
Okay, great. So a couple more questions here. The GPR that you guys used to try to locate rebar and other embedded items prior to coring, how deep can that GPR penetrate and locate items?
That is a very good question. I don't know the full answer to that. I know it can penetrate at least, I think it can penetrate up to a foot. So we obviously, what I assume the part of the point of the question is, you certainly can't GPR locate 17 feet into a structure. So we did the best we could, but yeah, there are limitations to GPR. I don't know, that technology is getting better and better. I know that and you can get a lot deeper, but I really don't know the answer to that. Actually, it's a good question as to what the limitations of that is.
And did you all do like an as-built or try to, do a post-mortem after you did a coring to determine what all rebar or other items may have been impacted by the coring?
We tried again. We could do that on the surface. Pretty tough to tell when 3, 4, 5, 6 feet deep into a structure. But no, we really couldn't do it in its entirety. And the main focus was to make sure we avoided any of the existing post tensioning. Obviously, that was a deal breaker. And we tried to avoid as much the reinforcing steel as possible. It's impossible to say we weren't going to catch some of the post tension, but yeah, it would have been nice to see how much was done, but I really don't know how that really could have been done accurately with the depth of the coring that we did.
Hmm. Okay, just a couple more questions and then we'll finish up. The size of the top slab access openings that were opened up as a process of the repair looked like they were fairly large, at least in terms of top slab access openings. Was there any top slab transverse post tensioning or even longitudinal post tensioning that was impacted by opening up those access holes?
Longitudinal, no. Transverse, yes. I believe the rule or the sort of guidance in the plans were, they were allowed to impact one tendon with those access. So they were strategically located that we didn't impact more than one transverse tendon. And so that was just sort of taken into account with when they were repaired back. But the longitudinal, no longitudinal tendons were affected.
Okay, great. And then one last question. The repairs on the top of the deck where the hanging bars went down through the deck looked like those repair areas were quite a bit larger than perhaps the sleeve that was needed for the hanging bars. Is that true? And if so, why were those repair areas so large?
They were. I think it just kind of had to do with the fact with the assembly of the hanging bars. They needed needed to chip down to basically, you know, I don't remember exactly what it was, but have a nut and a plate, and basically to have a proper assembly, they needed sort of that extra room. And you're right, it was each one was, I don't know, maybe probably like 1.5 by 1.5 feet. They weren't full depth; they were minimal depth, but yeah, it just had to do with the assembly of the hanging bars themselves and getting those pieces together.
Fantastic. All right. Well, that'll do it for questions for today. Tim, once again, thank you very much for a great presentation, and thank you to our audience for some really great in-depth questions. I'll just remind you that the certificates for attendance for this webinar will come out in about a week or so, and ASBI will also publish the slides from this presentation. You'll be able to find those on the website, and that information will be emailed out to everybody as well. So once again, thank you everyone for your attendance today, and we hope to see you in March for the discussion about lightweight concrete. So everyone have a great day. Thank you.